Okay, today we're going to talk about applications of some of these linear systems, and you guessed it, more word problems. Lucky you guys. So we're going to just go ahead and jump right in with some of these word problems. And these are in the 6-4 examples. And in this first one, a fashion designer makes and sells hats. The material for each hat costs $5.50. The hats sell for $12.50. The designer spends $1,400 on advertising. So how many hats must the designer sell to break even? So we want to know when to break even. We want to know when the costs will equal the income. Okay, so when we do this, we'll figure out the costs first. So we'll set the costs, and the cost for each hat for making these hats is there's a $1,400 initial charge for the advertising, and there is an additional fee of $5.50 per hat. Okay, so the total of the costs for making all these hats is $1,400 plus 5.5 times the number of hats that are made, because that's the cost per hat. Now the income is equal to what's brought in. So the hats sell for $12.50 per hat. So the total income would be 12.5 times the number of hats sold. So we want to know, when will this hat maker, hat designer, break even? So when will the cost, which is equal to 1,400 plus 5.5h, when is that equal to the income, which is equal to 12.5h? So first thing we want to do to solve this is get the h's on one side by subtracting the 5.5h. And from that, we have 1,400 is equal to 7h. And when we divide both sides by 7, this designer needs to sell 200 hats in order to break even. All right, the next one is very similar to this. We've got another breaking even problem. A puzzle expert wrote a new Sudoku puzzle book. His initial costs were $864, and binding and packaging was 80 cents per book. And the price of the book is $2. So how many copies must he sell in order to break even? So we want to know when costs, again, equal income. And so what's the total cost? Well, we have initial cost here of $864 plus 80 cents per book. And then the income is equal to $2 per book. So setting these equal to each other, cost, which is $864 plus 80 cents per book, is equal to the income, $2 per book. So then to solve this for b, we get the b's on one side by subtracting 0.8b. So 864 is equal to 1.2b. And then to divide 864 by 1.2, we get 720. So this puzzle expert needs to sell 720 puzzle books to break even in order for his costs to equal his income. Alright, so a local zoo is filling 2 water tanks for an elephant exhibit. One water tank contains 50 gallons of water and is filled at a rate of 10 gallons per hour. The second water tank contains 29 gallons of water and is filled at a constant rate of 3 gallons per hour. So when will the tanks have the same amount of water? So tank 1 has 50 gallons in it and is filled at 10 gallons per hour. Tank 2 starts off with 29 gallons and is filled at 3 gallons per hour. So when will tank 1 be equal to tank 2? So when will 50 plus 10H equal 29 plus 3H? Getting the H's on one side by subtracting the 3H, we get 7H. And subtracting the 50, that's equal to negative 21. So H is equal to negative 3. Well, since this time is negative, they will never have the same amount of water in them in the future. What this means is that 3 hours ago, they had the same amount of water. That's what the negative time represents. And the zoo has 2 other water tanks that are leaking. One tank contains 10 gallons of water. First tank has 10 gallons of water and is leaking at a rate of 2 gallons per hour. And the second tank has 6 gallons and is leaking at a rate of 4 gallons per hour. When will the tanks have the same amount of water? So when will tank 1 equal tank 2? And that happens when 10 minus 2H is equal to 6 minus 4H. Add the 4H to both sides and subtract 10. And again, we get H being negative 2, which means that 2 hours ago, was when they had the same amount of water in them. Alright, then the next one deals with wind speed and airplanes. We will have some similar problems to this with current and so on, downstream and upstream. Okay, traveler flies from Charlotte, North Carolina to Los Angeles, California. At the same time, another traveler flies from Los Angeles to Charlotte. The airspeed of each plane is the same, and the ground speed of each plane is shown below. So airspeed is a little bit different than what the speed is relative to the ground. Now, the red arrows here represent the wind, okay? And the wind is moving easterly at a certain rate, W, and we're not sure what the airspeed of these planes are. Now, if you think about this plane from Los Angeles to Charlotte, the wind is pushing it. The wind is helping it. It's speeding it up. So what we'll do is that the actual ground speed of that plane is actually the airspeed of the plane plus the wind, because the wind is helping it. And the ground speed is equal to 550. Now, when we start doing boat in a current and so on, the current going downstream helps the boat. It speeds it up. Going upstream, the current slows the boat down. So it hinders its speed. Now, our second plane going from Charlotte to Los Angeles is flying into the wind. So the wind is actually slowing the plane down. That's why we subtract the W there. And the actual ground speed of that plane is 495 miles per hour. Now, this is a perfect one for elimination, because when we add these two equations together, the W's eliminate, and when we add these two together, we get 2A is equal to 1,045. So the airspeed of each plane is A. So we take 1,045 and divide it by 2, so the airspeed of each plane will be 522.5 miles per hour. And then the wind speed, when we take 550, if we put that in, 522.5 plus W is equal to 550. So then the wind speed moving easterly is going to be 550 minus 522.5, and we end up with 27.5 miles per hour. Now, the last one is upstream and downstream, as promised. You row upstream at a speed of 2 miles an hour and the same distance downstream at a speed of 5 miles per hour. So going upstream, let's say you're in a boat, going upstream, the current hurts you, slows you down. That's why we subtract the C. Going downstream, the current is pushing you, so it's speeding you up. That's why we add the current. Now this is a perfect elimination problem, because when we add those two equations together, the C's cancel, so we have 2B is equal to 7. So if you were in the boat in still water, you would be traveling 3.5 miles per hour. And then to find the speed of the current, we can take that 3.5 and substitute it in for B. Plus the current is equal to 5. So when we subtract 3.5, C is 1.5. The rate of the current is 1.5 miles per hour. Okay, so that's setting these up. And again, the way you learn how to do these is just to practice them. So in class tomorrow, you're going to get a worksheet with a bunch of these word problems on them.